America is returning to the moon to build a permanent human base. This transition from theory to reality is currently taking place in clean rooms across the country, where engineers are already assembling the flight hardware for these upcoming missions. Building a permanent presence is a massive logistical challenge that requires continuous power, heavy surface infrastructure, and high bandwidth data. You cannot fit all the necessary equipment for a sustainable base onto a single rocket launch. This diagram shows NASA's strategy for Phase 1. Instead of a single mission, the agency is planning more than 20 separate lunar landings. To execute this, they are relying on a decentralized network of commercial space companies to deliver the equipment. NASA is essentially acting as a general contractor. They are dividing the workload by assigning specific technical responsibilities to different private firms, spreading the operational risk across a network of specialized builders rather than relying on a single failure point. Before heavy construction begins, NASA needs to map the hazards of the lunar terrain. Firefly Aerospace is preparing one of the first Scout missions with their Blue Ghost 2 lander. Blue Ghost 2 is headed for the far side of the moon. Its primary objective is to deploy the LuSEE-Night radio telescope. This schematic shows why the far side is necessary. The mass of the moon acts as a physical shield, blocking radio interference from Earth. In this protected zone, the telescope can observe the cosmic dark ages without signals from our planet drowning out the data. While Firefly explores the far side, Intuitive Machines is preparing the IM-3 lander to scout the near side. They are targeting a magnetic anomaly known as Reiner Gamma to study its environmental effects. These targeted scout missions provide the intelligence foundation for the entire project. By mapping environmental quirks and resources first, NASA can ensure that heavy infrastructure is eventually placed in the safest, most productive locations. The project eventually transitions from gathering data to physical construction. This stage requires infrastructure-class landers, vehicles designed specifically to transport massive cargo. At the Jet Propulsion Laboratory in California, Voyager Lunar Systems is putting their Griffin 1 lander through mass property testing. This ensures the vehicle's center of gravity is precisely understood before it carries its first heavy load. Griffin 1 is tasked with delivering the Astrolab FLIP rover to the lunar South Pole. The rover is the largest commercial payload ever destined for this region, and the lander must navigate harsh, cratered terrain to deliver it safely. Simultaneously, Blue Origin is testing its Blue Moon Mark 1 lander in Florida. This vehicle is proving out the liquid oxygen and hydrogen systems required to offload large amounts of cargo and precision manned in tight corridors. These heavy haulers are the bridge to a permanent base. Without vehicles capable of delivering significant weight and offloading it autonomously, lunar activity remains limited to small-scale scientific sensors. The lunar South Pole is home to extreme environmental stresses. Temperatures there can swing from 130 degrees Fahrenheit in the sun to negative 334 degrees in the shade. These thermal shifts will instantly destroy standard electronics. To survive, the power, communication, and landing systems must be hardened against these rapid, violent temperature cycles. NASA is partnering with Northrop Grumman on new technology demonstrations to address this. These missions are designed to test hardware specifically engineered for these temperature extremes. Their strategy involves repurposing durable components. They are adapting the power, avionics, and communication systems originally designed for the Gateway Halo module to function on the lunar surface. These survival systems act as the base's foundational infrastructure. Without power and communication links hardened to survive these thermal cycles, even the most sophisticated landers and rovers are immediately rendered inoperable. By utilizing a multi-company approach, NASA can execute rapid iteration. Problems found by one team can be addressed across the entire commercial supply chain simultaneously. Companies like Intuitive Machines and Firefly are already incorporating performance data from their first flight attempts into their next generation of landers, ensuring each mission is more reliable than the last. Evidence of this progress is visible right now. Engines are undergoing hot fire testing in Texas, and teams in Houston just completed thermal vacuum tests to simulate the lunar environment. This strategy is a departure from the Apollo playbook of the 1960s, which relied on a single, massive national effort to complete a short-duration visit. The new objective is to establish a resilient commercial supply chain. By delivering specialized infrastructure one lander at a time, NASA and its partners are building the foundation for a permanent human presence on another world.